Or why is it not valid? Okay, why is it not valid? Right? Why is it not valid? Right? So this is because the deformation in buckling is not parallel to the centroid or to the axial direction of the structure. Okay. So now, what do I mean by that? Everyone is using an iPad. Yeah, I need that. Wait, what type of paper? This paper is going to kill me, but good, if you don't mind. Thank you. Right, paper. Paper are not made by mechanical engineers. This paper is very thin, Sunshine. You are killing me, man. Okay, this paper is not made by mechanical engineers. Mechanical engineers, we don't make paper. What do we do? Any idea? We are tasked to do what we were given and stop bitching. Yes or no? Right? Paper. So in axial loading, right, is in tension, right? The material will fail in the axial direction. In buckling, not so, okay? So we are engineers, right? If you ask a lawyer, can paper support the wallet? The lawyer will say, how much? The more you pay him, the more convinced he will tell other people that it's possible. As engineers, we can't do that. So material science developed paper, or scientists develop paper, and paper cannot support my wallet, right? You know I let go, will collapse. So what engineers tend to do is we do 3CO3. What am I doing now? Manufacturing. IN folding. So when I fold, what is happening? Anyone? What am I changing? Mechanical properties is still the what? Same. Yes or no? Right? Material properties did not change at all. It's still the same. Right? Still a piece of paper. Now we change the geometry through manufacturing processes. So when we do this, right, paper can support, I told you the paper was weak. It's okay. It did not work yet. So what do? We do some other stuff. Okay? We fold more. Right? By folding more, if I look at the cross-sectional area, right? I mean, I don't want to do the calculation, it's not straightforward. We are also changing the second moment of what? Area. Okay. Oh man, I am doubtful about this. You know, this is not like a cooking show, you know. You don't know what I mean by cooking show. It's okay, okay. If this does not work, I will stop teaching buckling. Okay? So we keep on changing the cross-sectional area, right? We modify it. Okay, that's what mechanical engineers are all about. To make matter worse, this is more a civil engineering problem. What makes mechanical even worse is this bloody thing is moving. Okay, I'm not doing the moving part. Okay, how I wish I have another term with you guys. Then we incorporate motion, but not this. Now, how the structure will fail is different now. Okay, so I will turn to the other side for you guys. Okay, and hey, this structure is at the boundary. Okay, of failing. Okay. If you want, you can come to this edge and have a look. I want you to look at the edge. What can you tell me? Can you all see the edge? Can you see the edge? Now, how the edge is deforming, can you all see yes or no? Is it in an axial direction? Yes or no? It is not, right? Can you, I mean, too bad those online, you can't see this. Okay. Can you see this is buckling? Yes or no? It is like having this sort of curvature. Yes or no? Right? This is what we mean by buckling. So if we put more stuff, right? Good paper, you know. Son of the bitch. It's okay, okay. So I'll not waste your time, okay? It will fail, okay? Right. So now, now I have to delete the video where I use son of the bitch again. I have to. It's okay. I'm going to ignore it. So now you see what I mean by what? Buckling, yes or no, right? Those online, I'm so sorry, okay? You come to my office, I will show you buckling, okay? Right. So now we realize that equation 6 or whatever we applied before will not work, okay? Because everything is assumed to deform in its axial direction, right? Right? So now we are going to learn Euler's formula or formulation applied to buckling. And all this theory are developed before 1960s. Any idea why? All these great, fantastic ideas, even computers, are made before 1960s. Any idea why? No television. Okay, I'm serious, okay? Now we have television and internet. It's more destructive for our mental thought, okay? Okay, so I'm going to now sketch, okay, the deformation pattern during buckling. Okay. So as mentioned before, the L over A ratio has to be very big. So i.e., the structure is very long and thin. Okay. And then we have an axial load applied, right? And P is our axial load. Okay. And now this is our original length. Okay. So this is our L0 now. Okay. And over here we have our A, which is our cross sectional area. Okay. So if we were to look at our boundary condition, okay, if we look at a boundary condition, so we are going to take our original from the top. So on the top, I'm going to call this is our point of origin. Okay. Point of origin. Okay. Then I'm going to sketch a graph. And I think I need, yeah, this is okay. So over here, when x is equal to 0, y is also equal to 0. Okay. This is what we call our boundary condition number 1. Then our boundary condition number 2 is when x is equal to L0, right? Y is also equal to 0. So it has to meet this condition. Okay, it has to meet this condition. So when the structure deform, as you can see, you all can see the beveled region, right? We are going to make sure that it's an idealized case. Idealized case means the deformation is perfect. It looks like this. This is the assumption that we make. Okay. So we know if we were to pick a point, okay, if we were to pick a point over here, this is our point Q. Okay. And the distance from here to here, from this point Q, this is our X, okay, relative to point Q. And over here, right, I do apologize, I did not label this. So this is our Y. This is our Y. Okay. So if you look at how the structure has been deformed, right? If you look at the structures, how it's been deformed. So the deformation pattern, so over here, this is the mathematical description on how the material is deforming or deflection. Okay. If you look at this pattern, right, can you think of any situation where the deformation pattern is similar but not under axial loading? Anyone? You see this type of deformation pattern. In what? Yeah, bending. So if you look, so if we have a structure, right? Well done, okay? If we have a structure that is standing vertically, right? And one end is bolted in and one end, let's say, is pinned. Okay, right? And if we apply a load over here, P, right? In the horizontal direction, our deformation pattern will look like this. And this deformation pattern is due to what? bending moment. Yes or no? So the deformation pattern is the same for buckling and what? And bending moment. Now, you can see this deformation pattern that I drew down here is idealized. In reality, okay, it is not exactly the same, but similar. You can see how the paper buckled just now, right? It did not buckle in a perfect shape like this, did it, right? It buckled more on the center first. But we idealize it, okay? We have to somehow simplify it, okay? So now, if we consider point Q, okay, when we consider point Q, okay, let's look at point Q now. Okay? Now let's consider